In our do now, we're asked to simplify the expression using our exponent rules. So first thing I would do here is probably that power to a power, which would give us 2x cubed, because those parentheses are just grouping that statement together, x to the 8th over 8x to the 11th, which would then give us 2x to the 11th over 8x to the 11th. Our x to the 11ths are going to cancel each other out, leaving us with just 1/4. So something a little new with our exponents today is we're going to work on creating the same basis. So we want to think about for what value of x makes each of the statements true. So you might think about this as saying, oh, we know 4 to the 3rd has a value of 64. 2 to what power has a value of 64? So we can kind of count that out. 2, 4, 8, 16, 32, 64. 2 to the 6th has that power. So we'd say for the value x equals 6. But how we want to start looking at these things is to realize that the 2 to the x, that has a base of 2. Where here you have a base of 4. But 4 can be written as a base of 2, as just 2 squared. If we think of 4 as the base of 2, then 4 to the 3rd could be rewritten as 2 squared to the 3rd power, which is 2 to the 6th. And we can more easily see that, oh, this will work for a value of 6. Which really helps here because, well, I don't know what 27 squared is. I have no idea. But I can still figure out what value of x makes this statement true, that 27 squared is equal to 3x. Because I know 27 can be rewritten with a base of 3. 3 to the 3rd power is 27. So 27 squared can be written as 3 to the 3rd to the 2nd power. So rather than writing 27, we're writing 3 to the 3rd. It's equivalent with a base of 3. If we use our power to our power rule that we're keeping the base multiplying our exponents, we can see that it's 3 to the 6th. So that would mean, again, x equals 6. Just a coincidence that they were both 6. Our next example, is there a value of x that makes the statement below true? 4 to the 3rd equals 3 to the x power. This one, there is none. There is no value of x. And the reason being that 4 and 3 do not come from the same base. How in our previous examples, 2 and 4 both come from a base of 2. 3 and 27 both come from a base of 3. Okay? So what we're going to practice here is just taking values and rewriting them with a different base. And we're going to use our power to a power rule. Because if I'm taking 16 to the 3rd and rewriting it as a base of 2, I have to know, well, 16 is equal to 2 to the 4th power. So I can write 16 cubed as 2 to the 4th power to the 3rd power. And I would leave it just like that to show my work, and then just kind of use our power to a power rule, 2 to the 12th. Okay, so 125 to the 5th, base 5. I want to realize that 125 is 5 to the 3rd, and then we're going to do to the 5th power, so that would make this just 5 to the 15th. 16 to the 5th, now we're going to make it with base 4, not base 2 like we did in A. 16 is 4 squared, so that's going to be 4 squared to the 5th power, which would make that 4 to the 10th. For D, 25 to the x power, we're going to make it base 5. We know 25 is 5 squared to the x power. Now here we have a variable in the outside exponent. Still going to use our rules, keep the base, multiply the exponents. 2 times x is just 2x. That's our answer. E, a little more different. 9 to the x plus 3 power. We're going to rewrite it base 3. We know 9 is 3 squared, so that's going to be 3 to the 2 times x plus 3 power. Now, as we're doing our power to our power, we have to do 2 times x plus 3. That outside exponent is a binomial, so it's going to get multiplied by the 2 to both terms, giving us 3 to the 2x plus 6 power. So we're always looking to simplify there. And we see that again with f, with 1,000 to the 2x minus 3 power. And we're going to write that with a base 10. 1,000 would be 10 to the third power, and that's going to be raised to the 2x minus 3 power. So that's going to be 10 to the 3 times 2x is 6x. 3 times negative 3 is negative 9. Okay. So leveling up a little bit here, now we're going to look at pairs of numbers and decide what base to write them in so they have the same base. If we have 3 to the 4th and 9 to the 4th, that same base would be 3. So 3 to the 4th is good to go. 9 to the 4th, we're just going to rewrite as 3 squared to the 4th power, which would make that 3 to the 8th. So we've got 3 to the 4th and 3 to the 8th. 2 to the 3rd and 16 to the 4th, we can have both in base 2. 2 to the 4th is 16, so 2 to the 4th to the 4th power, that's going to be 2 to the 3rd and 2 to the 16th. Now C is a little different here. We've got 25 to the 4th, 125 squared. Now 25 times 5 is 125, but I can't write 125 as a base of 25 because it's not made from 25 times 25. But both numbers can be made from a base of 5. 25 we can write as 5 squared, so 5 squared to the 4th power. 125 we can write as 5 cubed, so 5 cubed to the 2nd power, which would give us 5 to the 8th. And 5 to the 6th. This allows us to easily and quickly compare which is larger, 5 to the 8th, because it has the larger exponent. Okay. D, we have some variables in our exponents now, 36 and 216. That's again, place where do we want to, what base do they both come from? That would be 6. 6 squared is 36, so that'd be 6 squared to the x power. 216 is 6 to the 3rd power to the x power, so that would be 6 to the 2x power and 6 to the 3x power. And then E, working with our 1,100 base here, those can be both written as base 10. 10 to the 3rd and 10 squared. Okay. Remember multiplying, so that's going to be 10 to the 6x minus 9 power and 10 to the 2x plus 1 power. And you might say, well, why are we even working to get to the same bases? Well, if we get our numbers to the same bases, then we can do our operations with them. We can multiply, we can divide, and so on. And that's what we're going to look at on the next page. Tomorrow, we're going to work up to being able to solve equations that have variables in the exponents so long as they have the same base. Okay? So here we have 4 squared times 16 to the 3rd. We're reminded our rule of multiplying with same bases that you're going to keep the base and add the exponents. But first, we need to have same bases. 4 squared and 16 to the 3rd, we can do those using same bases, right? Because 16 is 4 squared to the 3rd power. I'm going to simplify that. So 4 to the 6. 2 times 3 is 6. Now I'm multiplying with same bases, so now I'm going to keep the base and add the exponent. Some of you may have noticed that's not the only way we could have done this problem. We also could have taken this problem and we could have written it with a same base of 2, where we say 4 is 2 squared to the 2nd power, and 16 is 2 to the 4th, and then to the 3rd power, which would give us 2 to the 4th, times 2 to the 12th, which would give us 2 to the 16th. So either pathway and either answer would be accepted there. For B, 5 to the third times 125 to the fifth, right? We're just going to manipulate that 125 to 5 to the third to the fifth power. So it'll be 5 to the third times 5 to the 15th. Now we're multiplying with same bases. Keep your base, add your exponents. It's important that here we're remembering what rule we're using. So we know when we're multiplying exponents versus adding exponents, right? When we're doing power to a power or multiplying with same bases. We can do the same thing with dividing. Now here's where we're really going to stick to our rule of if we're dividing with same bases, we're going to keep the base and just subtract the exponents. Okay, it'll be nice and quick. 16 to the fifth divided by 2 to the fifth. We know 16 can be written as 2 to the fourth. So 2 to the fourth to the fifth power divided by 2 to the fifth power. So that would be 2 to the 20th divided by 2 to the fifth. Keep our base, subtract our exponents. 2 to the 15th. Okay. 9 to the third and 27 to the fifth. We're going to rewrite both as base 3. 9 is 3 squared, and then to the third power. 27 is 3 cubed, and then to the fifth power. So that's going to be 3 to the sixth divided by 3 to the 15th. Keep our base, subtract our exponents. 6 minus 15 is negative 9. So we just want to rewrite that as 1 over 3 to the 9th. You might be noticing and saying we're not fully simplifying. Well, yes, we're not fully simplifying. We're not getting to that number answer because we're really just focusing on manipulating the bases here. So we don't want to worry our brain power with what 5 to the 18th is or 1 over 3 to the 9th. So for today's lesson, that's fine. Plus, we're working up to now doing this with variables. So let's look at how this might change a little bit when we have variables in the exponent. We're still going to work to get to our same base, right? So for this case, that would be 10. 1,000 is 10 to the third power to the 2x minus 3. 100 is 10 squared to the x plus 1. Power times power, power to a power, we're going to multiply. So 10 to the 6x minus 9 times 10 to the 2x plus 1. Now we're multiplying with same bases. We're just going to keep the base, and we're going to add the exponent. So if you need to, go off to the side and add your exponents. And then you can see you're combining like terms to say, oh yeah, that's going to be 10 to the 8x minus 8 power. And see, that's something we couldn't simplify any further anyway. Okay. 4x to the negative fifth power times 8x plus times 8 to the x plus 1 power. We are going to get these bases to 2. We can't do 4 because 4 times 4 is 16, not 8. So 4 is 2 squared. So it's going to be 2 squared to the x minus 5 power times 8 can be written as 2 to the third to the x plus 1 power. So power to a power, we're going to multiply. That's going to be 2 to the 2x minus 10 times 2 to the 3x plus 3. Now we're multiplying with same bases. We're going to keep the base, add your exponents. So we'll have 2x minus 10 plus 3x plus 3. So we have 5x minus 7. So it'll be 2 to the 5x minus 7 power. Okay. And then our last two, we're just going to do with dividing. So that's going to be keeping the base, subtracting our exponents. But first, we're going to get them to the same bases. So for C, that would be 5. 25 is 5 squared. So 5 squared to the x minus 1 power divided by 125. That'll be 5 cubed to the x plus 2 power. Doing our power times a power. So 2 times x is 2x. 2 times negative 1, negative 2. 3 times x, 3x. 3 times 2 is 6. And now here with the division, keeping our base, subtracting our exponents. Here is where I'm really going to encourage you to go off to the side and do some of that scrap work. So you can see that we're doing 2x minus 2 minus 3x plus 6. Because we're subtracting a binomial, that negative is going to get distributed. So 2x minus 2 minus 3x minus 6. 2x minus 3x, negative x. Negative 2 minus 6, negative 8. So we're going to have 5 to the negative x minus 8 power. If you are not going to the side of your paper and doing this work out where you're seeing the distributing, you are really increasing your chances of making a computational error. So I'm going to model it again, D, showing all my work off to the side. 27 and 9, we can get to a base of 3. So that would be 3 cubed to the x plus 1 power divided by 9, we can write as 3 squared to the negative x minus 5 power. So it's going to be 3 times x, 3x, 3 times 1, 3, divided by 2 times negative x, negative 2x, 2 times negative 5, negative 5. We're going to keep the base and we're going to subtract our exponents. So I'm going to go off to the side again. Binomials in parentheses. Subtract, right? I'm following the order of my division. I've got to distribute my negative. So I have 3x plus 3 plus 2x plus 5. 3x plus 2x is 5x. 3 plus 5 is 8. So that's going to be 3 to the 5x plus 8 power. Okay, so everything for today, we're trying to get to same bases or a given base if you're told, and then looking at using our exponent operations to simplify to that one same base.